Hi everyone, welcome back to Chemistry 222. This is your first week. I'll be happy to be teaching you guys all about chemistry each week and going over some of the problems from the textbook. I linked the textbook URL in the chat below, so make sure to click on that so to follow along or go back to these questions and to go over any other problems you want to go over. We will be working from chapter 5 today. So we are going to be going over energy as well as calorimetry. This is chapter review. I'm not sure if you've started this yet in your classes or not, or gone over it in detail, but we will be going over about, I think, 7 questions. So yeah, let's get started. Okay. Hopefully you guys can see my screen okay. Everything is great. Okay, so as you can see at the very top, we are going to be going over chapter 5, like I said, and problems 6, 10, 18, 20, 24, 26, and 30. So these are the problems that are even, and so you won't get the answers in the back of the book like you do with odd questions. So this is nice to go over these specifically because you won't have the answer given to you already. So yeah, let's get started. First problem that we have is question 6. It asks how much heat in joules and in calories must be added to a 75-gram iron block with a specific heat of 0.449 joules per gram degrees Celsius to increase its temperature from 25 degrees Celsius to its melting temperature of 1535 degrees Celsius. Okay, so as we can see, or what we can notice is that what we're trying to find here is in the first part of the question. It says how much heat. So how much heat in joules. So that's also known as the Q value. So the equation that we'll need to use to find the heat is a simple simple equation. Q equals, I always remember as MCAT. So it's MC delta, so change in temperature. So I always think the delta looks like kind of like an A. So you could say Q equals MCAT. It's pretty easy to remember if you're having trouble remembering that formula. But that is the formula we need to use to solve this problem. And it also says we need to find the heat in joules and calories. So we'll need a conversion between joules to calories because Q right now, if we were to solve it for Q, it gives us a specific heat right here. And I can zoom in so you can see that better. This value right here is C, and it's the lowercase c. So there's a difference between the lowercase c, which is the heat or the specific heat, and the big C is the heat capacity. So that's a kind of a small difference there, but they will have different units. So that's how you'll know. If there is no change in temperature, it'll just be, I believe, let's see here, it's joules per gram instead of joules per gram degrees Celsius. So that's the difference between specific heat and heat capacity. So be sure to be aware of that unit change. And so let's go back to the question and see what other values we are given. So we're obviously given a mass. So that is 75 grams of this iron. And it also has a degree change to 25 to 1535. So we have all of what we need to solve this problem. So we have this equation here. So this is what we're going to start with. So Q is what we're finding. So we can just have it set equal to everything that we are given from the question. So M stands for mass. So that's the 75. We know what C is. And the delta T is the 25 to 1535. So that is the change. So for M, I'm going to be putting it in right here now so we can see better. So that is a 75.0, and this is in grams. So if we want to keep track of units, we can. I already know that everything's going to cancel out, but I'll just do the unit analysis to the side so you can all see that. It's good to do that and to make sure you're having things that check out. So if we have the mass given in grams, so it's just grams times C, which is the specific heat, which is joules over grams degrees Celsius, and then the change in temperature is going to be in degrees Celsius. And so everything will cancel, as you can see here. So the grams cancel out with grams, the degrees Celsius cancels out with the degrees Celsius. So we'll end up with joules. And so the question is asking the answer to be joules and calories. So we'll get an answer in joules, and then we'll need to convert it to calories. So let's put everything else into the equation right over here. So it's 75 grams times the C, which is the specific heat, and that is 0.449, times the change in temperature. So the delta T is the final minus the initial. So be aware of what temperature is going to what and what the final initial is, because if you swap it, you will get a negative value, and so it would look like the energy is the opposite. So instead of being endothermic, a positive Q value, it'll be exothermic, a negative value, and so it'll give you a different kind of sense of what's going on. So just be sure to do final minus initial, what you're ending up with. So that is going to be 1535 minus 25. And so we can calculate all of that out, and we will get a value of 50849.25. And so since we're given 3 significant figures for the least amount of significant figures used in this is going to be 3 sig figs. Our answer will also be in 3 sig figs for the joules, so that'd be 50800 joules. And so that is the answer of the heat that is needed to be put into the iron to bring it up to the melting temperature. And so now let's convert that back into calories, and make sure to use the one that you didn't round to, so that you don't get a wonky answer. So we started with 50849.25 joules. And so the amount of joules per calorie is 4.184 joules per 1 calorie. And so that will give us an answer of 12153.26. So with 3 significant figures as well, Q will equal 12,200 calories. So these are the 2 answers for this problem. Let me know if you have any questions so far. The first question is pretty standard for a lot of these energy calculations. This is kind of the more lower, or not lower level, but it's the fundamental basic of continuing on with these energy calculations. Because when you have like maybe 2 things together in a calorimeter, they're transferring heat to one another, and then it gets a little bit more tricky because you'll have more than one term. So we will see that in the next problem, actually. Okay, so let's move on to the next problem. This is problem 10, also from chapter 5. Everything's from chapter 5. And the problem reads, a piece of unknown substance weighs 44.7 grams and requires 2,110 joules to increase its temperature from 23.2 degrees Celsius to 89.6 degrees Celsius. What is the specific heat of this substance? Okay, so we're given the weight, so that's M. We're given Q, so we're not solving for Q anymore. And the temperature is increasing from 23.2 to 89.6. So that's our delta T right there. So we're giving 3 of the variables in our energy equation, but instead we are solving for the C, the lowercase c, the specific heat. So let's first set up the equation not solving for Q, but solving for C. So that'll look a little different. Q equals MCAT, as we know. Sorry, lowercase c. And so since we're solving for C, let's just divide some of these variables across the other side. So the C is on the right side. I'm going to keep it on the right side for now because it's attached to these 2 variables. It'll just be easier that way. So I'm going to divide both sides by M and delta T. Sorry, M and delta T. And so the M will cancel out, the delta T will cancel out, and we'll be left with C here. So it'll be C, Q over M delta T. And I usually like to solve for whatever I'm solving for on the right side of the equation, so I'm just going to switch this around, and it'll be C equals Q M delta T. So that is our equation, and so now we can just plug in all of our values we're given and solve for the heat capacity. Or sorry, specific heat. I'm even messing up with those 2 different C's. So let's plug in the Q. So the Q we're given as 2,110 joules, so let's plug that in. And then the mass is also in grams, so it checks out just as the last problem. 44.7. And then delta T, so it's the final minus the initial. And so right here in blue, I circled, it's 23.2 to 89.6. So it's going to be 89.6 minus 23.2. Okay, and calculating this out, I already calculated this out earlier, so I already have it planned. So that is going to be a value of 0.711, and that is rounding with the 3 significant figures as well. And the final units will be joules per grams degrees Celsius. Okay, that is the answer to part A. Part B asks, if it is one of the substances found in table 5.1, what is its likely identity? I already looked at table 5.1. It's in the chapter, as I was saying, and the link shows, a table of different values, and it's the closest one to 0.711. It's pretty easy to find. It's just right there on the table. It's silicon. I never know if it's pronounced silicone or silicon. I feel like that's still a debated topic, or maybe I just don't know how to pronounce it. But yeah, it's silicon, and it has a very close specific heat. Yes, 0.712 joules per gram degrees Celsius. So that is the answer to B. Okay, awesome. Let's move on to the next question. Okay, this one is problem 18, and it asks how many milliliters of water at 23 degrees Celsius with a density of 1.00 grams per milliliter must be mixed with 180 milliliters, about 6 ounces, of coffee at 95 degrees Celsius so that the resulting combination will have a temperature of 60 degrees Celsius. Assume that coffee and water have the same density as and the same specific heat. Okay. Just to clarify, I probably could use some coffee right now myself, but let's solve this problem. Okay, so it asks us how many milliliters we need. So we first have to understand that the density is really important here, because in our Q equals MCAT, for M, it's going to be in grams. So we're not working with milliliters like it's giving us. We're going to be working with grams. So that's the first kind of thing we need to recognize, making sure our units kind of check out and solve that first before moving on, like, setting up our equation our units and then plugging things in, because then we can like go back easily and see where we went wrong possibly, because it'll be right there in the beginning of like how we set it up. So that's the way I like to do it. So we know that the water has to be 23 degrees Celsius, right? And they both go to 60. So the coffee's at 95, water's at 23, and they both go to 60. So these are the changes in temperature of the water and coffee. So let's write that down first. So delta T, and make sure to write down here or below which one you're talking about, so that you don't cross-track different values that you're calculating for. So delta T of coffee, so they both want to end up at 60. So that'll be the final temperature. So I'll just write that down here. Delta T of water. So 60 minus 23 is what the water was at, and the coffee was at 95 degrees. And just a quick side note, these all changes in temperature, I'm using Celsius because it's a change in temperature. It's more of common practice. Just ask your teacher like maybe what they would like to see, and have you like develop as like a habit, changing between Celsius and Kelvin. The reason why it's going to work out the same, because delta T has to do with the difference value. So the reason why it's the same is because when you add between Celsius and Kelvin, you add 273.15 degrees to make it to be degrees in Kelvin. And so because you add 273 degrees to each one of these values, so if we added it to 60 and we added it to 23, it would just cancel each other out and we would have the same delta T value. So that's the reason why I'm not putting it in Kelvin before finding the change in temperature, because it's not that important for the math wise, but for understanding sometimes it can be better. And also in this problem, the specific heat, like in the last one here, it has per degrees Celsius, so you can keep it in that because it's kind of it's working with that change in Celsius degree. But if that had a K there, it would really be the same kind of thing like I was saying. So just keep that in mind. The difference in temperature of Celsius and Kelvin technically is mathematically the same, but there's still some debates about that. But anyway, that's just a side note. So we have the difference in coffee and water, so let's just subtract these two. So this will be negative 35, and then this will be 37. So keep in mind that this has a minus. And so both of them have the same density and same specific heat. So because they have the same density, and the density of the water is 1.00 grams per milliliter, it's just a 1-to-1 ratio between liters and grams. So because we're working with 180 milliliters of coffee, of coffee, yes, it's going to be the same thing. So yeah, so it's 180 milliliters of coffee. Okay. So the amount of mass of coffee will be 180 grams, and we want to find the water. And so whatever gram amount we get will be equal to whatever milliliter amount it is asking for. So just keep that in mind. Okay, so that's that, and let's see. We have the temperature out of the way, the density is the same, and we have the specific heat. It's the same for both, and the specific heat of water is going to be C equals 4.184 joules per gram degrees Celsius. So that is the C value here. And so it looks like we have everything out of the way in terms of writing down all of what we have from the equation here, or from the problem. So let's write down what we would need to set up the equation. So in order for energy to be conserved, we have to set these two different energy values to 0 because they are transferring the energy to themselves. So Q of water plus Q of coffee will equal 0 because they transfer their energies to each other, so there's no ending difference because you can't create energy and you can't destroy it, as we know. So all we have to do is just replace these Q's with what they are equal to in terms of an equation. So that would be the MCAT. So that would be MC delta T, and this of water, plus MC delta T of coffee. So that will equal 0. And so let's put in all these values for this. And so Q of water we are solving for. So that'll be M, and then C, the C value is what we're given as the 4.184 as we wrote down earlier, and times the 37, which is the difference in temperature. So 37, and that's plus the M value, so that's 180, this is of coffee, times the C, 4.184. I'm going to move this to the left a little bit. And then times the delta C, which is the negative 35. And that'll all equal 0. And so let's just do this right here. Okay, and so since we're solving the M of, I'll write down that this is W, we can put everything to the right side. So if we subtracted this whole term, it'd be 180 times 4.184 times negative 35. And then this would need to be divided by this term to then have this equal to MW. So that'd be 4.184 times 37. And so if we looked at this here, we could notice that this negative is right there, so that we can bring that out. Both of the 4.184s are canceled out, so we can simplify down at what we're multiplying here. So it's 180 times 35 over 37. And multiplying all this out will give us a value of 170.27027. And so since we're working with, I believe only two significant figures at least, we will have our answer also in two significant figures. So this would be 170 grams. And so just as we said before, since the density in the question, it says the densities of the coffee and the water we're assuming is the same. It's not going to be because coffee will make it slightly, a little bit more dense. So, but we're negating that fact. So 170 grams is also equal to 170 milliliters of water. So that is how much, or that is the quantity of the water that is needed to have those have the final temperature be 60 degrees Celsius. So if you ever want to be super accurate with your coffee making, you can use these equations to solve for whatever you're trying to do. Okay, so let's move on to question 20. And let me know if you have any questions during this process as well. So this problem reads, a 45-gram aluminum spoon, specific heat, 0.88 joules per grams times degrees Celsius, and it's degrees Celsius as well, at 24 degrees Celsius is placed in 180 milliliters, 180 grams, of coffee at 85 degrees Celsius, and the temperature of the tube become equal. Okay, so the first question is, what is the final temperature when the two become equal? Assume that coffee has the same specific heat as water. Okay, so it's a coffee problem just as last time. And so it'll have a similar kind of style to what we did. There's a spoon, so it's metal. So metal and then the coffee are transferring heat to one another. So energy is conserved. always is conserved, but how we set up the problem is going to be equal to 0 because they're transferring to each other. If, for example, this question was talking about how something is cooling down, like how much heat is being given off, we don't set that equal to 0. Just keep that in the back of your head, because it's important, the surrounding and the environment of these questions. So because they're with each other, they're transferring to each other, we can do this just as we did last time. So it's Q of metal plus Q of coffee equals 0. So you can probably assume where we're going, or maybe not, but that's fine. So we'll put the equation for Q into each of these terms in terms of the metal, what's going on with that, and what's going on with the coffee. And so the specific heat of the aluminum we're given, so that's the C value. We're given the M value, that's the point, or the 45 grams. And so the delta T we don't know, but we know its initial value was at 24 degrees Celsius. So that's T, we'll say initial, we have. So we don't know the T final. And so for C, it's also 4.184. That's just a common, that you'll need to know the C value of water. You'll probably be given that in a problem, but it's just good to know that is the specific heat of water. So that's 4.184. So we have it of the coffee water, same in this problem. And we're also given the amount of mass, the 180 milliliters or 180 grams. And we're given the initial temperature, which is 85, but we don't know the final. So that is what we need to find in both of these. And they share that value anyway, so we are going to write out this equation and then solve for TF on one side to make it a little bit more simple because it's in both terms. The last problem, only this was in one of the terms, so it's kind of easier to solve for once you plug in everything. But if TF is in both terms, it's kind of better to set up everything to solve for TF algebraically before you start plugging things in, but that's just a matter of how you like to solve for things. So we're just going to go ahead and do that. So for the Q metal, we have C, or MCAT, so it's MC, and instead of delta T, I'm going to write TF minus T initial here. And that's also the same thing. C, this is lowercase c, TF. Oh, minus T initial equals 0. So let's just move everything over. Oh, and because we're solving for two different things, or two different Q's, I'm going to put little M's underneath this so we know what we're talking about. It's TIM, MC, CC, TIC. Okay, so let's solve for everything over here. So we can first subtract this on both sides, so, or one of these terms. So it can look like MC, I'm just going to keep the coffee one over here, MC, CC, TF minus TI, like that, equals MM, and that'll be negative CM TF minus TIM. Okay, I'm going to double check I did that right. Yep. Awesome. And so let's multiply these terms out so that we're working with not this whole thing coupled in these parentheses here. So that's going to be MC, CC, TF minus TIC, and then MC, CC. And then over here on the right, it's going to be MM, CM, TF. And then because there's a minus, this will cancel out. Move everything over. So that'll look like a positive MM, CM, TIM. So Tim will be over there. Awesome, just making sure I did my math correctly. Awesome. Okay, and so keep in mind that we're solving for the TF, so it's located over here. So I'm going to move the other terms that don't have that on the same side. Okay, so let's do that right now. So I'm going to move this term over here and then that one back over there. So this will have TIC MCCC plus MMCM TIM, and then adding that over here, MCCC TF, and then adding that term, so it's MMCM TF. Awesome. And so because TF is on both of these sides, I can have it be distributed to both of these terms, so then I can just divide by everything. I'll show you what that looks like. So the TF is multiplied to this and this. So we'll just do MCCC plus MMCM. And then this will be repeated here. And then we'll divide this term on both sides. So this will be again repeated, and then we'll divide it by this. There we go. Okay, so now we have the equation for TF, and if this was like, if you don't like to have the equation set up, you don't have to. You can just plug in everything equation here and then solve for TF if you want to work with actual values. Go ahead and do that. I wanted to show both ways and see whichever way people wanted to go for. So let's plug in all these values that we know. So the initial value of the coffee is going to be at 85 degrees. The mass of the coffee is, I believe, 180. Yes, 180. The heat capacity is specific heat is 4.184. So that's the first term here. And then the mass of the water is going to be, the mass of the metal is 45 degrees. And then the specific heat is 0.88. And the initial temperature is 24 degrees. So let's divide by the mass of the coffee, which is 180. I'm just seeing if I did that right. And then multiplying that by the specific heat of the coffee, which is 4.184. And then adding the mass of the metal and heat capacity again. There we go, and it's it's 45 times 0.88. Okay, that was a lot of work, but that's okay. And we'll move this over to here. And so I already worked this out earlier, and so the final value will be TF will be equal to 81.952770, but we can round that. And because we're working with two significant figures, this will be a final answer of 82 degrees. So that's what you should get at the end of all of that. Awesome. So yes, let's move on to the next problem or the next question. And I believe this is a continuation of the same question. And so it asks, the first time a student solved this problem, she got an answer of 88 degrees Celsius. Explain why this is clearly an incorrect answer. I can answer this pretty quickly, actually, because it's actually more apparent than you might think, because 88 is so close to 82 of the answer that we got, but there's a reason why. So the Q values that we have right? It's a QM plus QC equals 0. For the delta T value, the final, or the Q plus Q will have to equal 0, right? So both of these terms, they have to add up to 0. So they both can't be positive terms and they both can't be negative terms. One has to be positive, the other one has to be negative. So the only way of switching signs in this problem is the change in temperature, because if your final temperature is lower than what you were initially at, it's going to be negative, and vice versa, it's going to be positive. So that's how we can know if our terms are going to be positive or negative, or the source from that. It's from the change in temperature. So if you had the QM value and the QC value for the delta T's, if it was 88 and the initial value of the metal was 24, and the initial value of the coffee was 85. This is just to see if this is positive or negative, these terms. This is a positive, and this is also a positive. So this cannot equal to 0 because these two terms cannot equal to 0. So it's clear, it's just simply as that. So if you wanted to check maybe if you were, getting the right answer, look at your delta T values, and it would have to be at least 24 here, 24 to, actually, it'd need to be 85, or a little bit more than, less than 85. That's less than 85. That would be the needed temperature if this word was to be correct. So there you go. That is the question or the answer to 20B. Let's move on to 24. So this question reads, a 0.500 gram sample of KCl is added to 50 grams of water in a calorimeter. If the temperature decreases by 1.05 degrees Celsius, what is the approximate amount of heat involved in the dissolution of the KCl, assuming the specific heat of the resulting solution is 4.18 joules per gram degrees Celsius? Is the reaction exo or endothermic? So just to answer the last question real quick, or just to clarify what these mean, exothermic means we will have a negative Q value, and endothermic means it'll have a positive Q value. So whatever heat answer that we get, that's what it's asking for, the Q value. If it's positive or negative, it'll already respond to that question without us really having to do anything. So let's mark down all of what we got here. So this question is involving something that all things involved decrease by a certain amount, and the final solution specific heat. So we only have one term to calculate for because we already know the amount of mass of both. We have the change in temperature, and we have the specific heat. So all we have to do is just have Q equals MCAT and put in those MCAT values, and we'll get a Q value. So let's write that down. So Q equals, MC delta T. And this is of the KCl plus the water. Labeling it helps to, as we know, helps to keep track of everything. So the M value here is going to be the addition of both of those weights, and so that was the 0.5 grams and the 50 grams. And they're both in the same units, so just in case you wanted to check to see if you're in the same units, we are. So it's 0.500 plus the 50.0. That is the mass, and then multiplied by the C value, which is going to be the 4.18, and the delta T. It already gives us the change in temperature. It doesn't give us initial or final. It just tells us, what's happening. So it's going to be the negative 1.05, since it said it's decreasing by that change in temperature. So multiplying all of that out, we will get an answer of negative 221.6445. And because this is negative, let's actually round this first. This is negative 2, 2, 2, and we have 3 significant figures throughout this as well. And because this is negative, this is going to be exothermic. Because it is releasing heat. It does not need to, if it would be positive, then it would be putting heat into it, but it's going to be releasing heat because it is losing temperature and all that jazz. Okay, so let's move on to the next problem. This is going to be problem 26, and I believe we have 2 problems left for today. Okay, this one reads, when 50 grams of 0.200 molarity of sodium chloride, it's an aqueous solution, at 24.1 degrees Celsius is added to 100 grams, so also grams, of 0.100 molarity of the AgNO3 at 24.1 degrees Celsius in a calorimeter, the temperature increases to 25.2 degrees Celsius as AgSCl forms. Assuming the specific heat of the solution and products is 4.20 joules per grams degrees Celsius, calculate the approximate amount of heat in joules produced. Okay, so the final statement tells us what we need to solve for, the amount of heat in joules produced. And because our heat capacity, specific heat, I keep doing that, specific heat is in joules, we won't need to do any unit conversion there. So this is both, just like the previous problem, it is going to be a single term of finding the Q value because nothing is transferring to one another. Both of these things, or it's giving us values from the question of what's happening to both. So it's already kind of taking into account the transfer in between each other. When we have a Q value that's, like our terms not equal to 0, it just means it's going to be transferring its energies maybe to its surroundings, and that's kind of more difficult to kind of account for because the air is different in different places, humidity is different in different places, so it's kind of hard to calculate, how the energy in the surroundings can look like. So besides that fact, we have one term we're working with. So this is going to be Q equals MCAT. And so since it is equal to Q, we don't need to divide by any of these terms to solve for anything else. So it is already set up for us. And so this question is a little bit different because it's giving us molarities for these products here, and that may look a little bit confusing to look at, but forget about the molarities in this. It's only talking about the amount of mass. So we have 50 grams of this, of the NaCl, and we have 100 grams of the AgNO3. So in total, we have 150. So that is going to be our mass value. And so for the C value, it's the specific heat, already gives us the value, so it's going to be 4.20. And the delta T, it says at 24.1 degrees Celsius in a calorimeter, the temperature increases to 25.2. So those are the 2 temperature values for our delta T. So it increases to 25, so 25.2 is our final value, so minus the initial, which is 24.1. And so solving for all of that, we will be getting a value of 693 joules. And we're working with the 3 significant figures here because that is the smallest amount that we were working with. So that is the answer. Seems a bit more tricky than it actually is, in my opinion, when it adds molarities. But yeah, so let's move on to the next one. So this is problem 30, and it asks, when 1.0 grams of fructose, C6H12O6 solid, a sugar commonly found in fruits, it's It's wonderful, isn't it? Is burned in oxygen in a bomb calorimeter, the temperature of the calorimeter increases by 1.58 degrees Celsius. If the heat capacity of the calorimeter and its contents is 9.90 kilojoules per degree Celsius, what is Q for this combustion? Okay, so we first should notice that it says heat capacity, not specific heat. And it goes along with the units I was talking about earlier, how heat capacity doesn't have a change in, or doesn't have a mass located next to it. So let's set up this problem. So it's asking for Q, just as usual, but we won't need a mass connected to it. So it'll be Q equals C delta T. And it does say there's 1 gram, so even if you accidentally multiplied by the mass here, it wouldn't change anything, but just keep that in mind. So the delta, or the C value that we're given, is 9.90, and the delta T, it increases, so it's positive delta T of 1.58. And so that's all that is needed to solve for this. And multiplying this out, it'll give us an answer in kilojoules. So it's 15.642 kilojoules. And rounding to, I believe there's 3 significant figures used. Yep. This will give us an answer of 15.6 kilojoules. So that is the answer to the last problem for today. And again, let me know if you have any questions to any of these problems. And hopefully this helped you with figuring out a lot of these different kinds of energy questions that you'll get faced in your future chemistry classes and courses. Yeah, and so I will see you all next week if there are no questions. And I hope you guys have a great weekend and your week is off to a great start of the school year or school term. I will see you guys all next week.